Hi, let me share my screen. Thank you so much. I am Armando Gallegos. I come from the Universidad de Guadalajara, Mexico, and I am going to talk about existence, uniqueness, stability, and numerical preservation of positivity in a time-delayed reaction diffusion epidemic model. This is the outline of the talk: motivation and background, mathematical model, positivity and abundantness, existence and uniqueness, stability analysis, numerical scheme, numerical simulations, and conclusions. So the idea is to study this disease, HIV, in the epidemiological context. So this disease has major transmission routes like sexual contact, shared contaminated needles, vertical mother-to-child transmission. Essentially, we have two management pillars, non-pharmacological and pharmacological, and many existing models omit the time delay factor that it gives unrealistic results. The key challenge um, of this disease is departs greatly from conventional infectious diseases, creating novel problems for epidemiologists, biologists, and mathematicians. So in this work, we extend a classical late ordinary differential equations model to a spatial temporal reaction diffusion framework and rigorously analyze its mathematical and numerical properties. Okay, why delay is important for us? Okay, incubation period. Infected individuals are contagious before symptoms appear. The exponential factor accounts for natural mortality during the latent window, and delay models better match observed epidemic curves. Uh, if we extend to the spatial diffusions, of course, the disease spreads at different rates across regions. A purely temporal ODE model assumes homogeneously mixed populations, which is unrealistic, of course. Reaction diffusion partial differential equations capture geographic heterogeneity. So our objective is to construct, analyze, and numerical solve a four-compartment delayed reaction diffusions HIV epidemic model that preserves positivity, establishes stability thresholds, and proves existence and uniqueness via fixed point theory. So um, the idea is to use the compartmental structure where we have susceptible population, infected, asymptomatic, and managed population, where the key parameters are transmission rate, contact rate, transfer to asymptomatic, transfer to managed, treatment rate for asymptomatic individuals. This parameter is very important. So in order we have the transition to asymptomatic to infected, uh, new natural death, disease death, delay, of course, recruitment rate of population, modification parameter for transmission for asymptomatic individuals that is included in this part, from susceptible to infected. Uh, the idea is to propose the following system of ordinary differential equations that is based on uh, this uh, reference. But we include the incidence terms where the time delay is included. But the idea is to expand to the reaction diffusion extension. So the previous system is expanded to this partial differential equation system where the diffusion terms are included and of course the partial derivatives. And we propose the following boundary conditions, homogeneous Neumann, of course. And non-negative initial data, of course, for realistic EV conditions. So we can notice that the A compartment, the managed population, cannot be seen among the first three equations. Note that the A is not in the first three equations. So we omit this compartment. Okay. Uh, Essentially, we have two equilibrium points. This is free equilibrium, yeah, and the endemic equilibrium. And the very important value in this type of system is the basic reproductive number, which is computed via the next generation matrix method. And we obtain this result, where if this value is less than 1, the infection dies out. And if this number is greater than 1, the disease persists. Of course, if the diffusive parameters are equal to 0, these systems reduce to the original ordinary differential equation system, or purely temporal. Okay, for the positivity of the solutions, we use this lemma, because this lemma is the main analytical tool for establishing positivity of each compartment. Okay, the main theorem about the positivity is that if the initial conditions are positive, then all solutions of the reaction diffusion system remain positive for all the domain. Here, the proof sketch is as follows. From the S equation of the system, we can establish this inequality. So if this inequality is satisfied, all the hypotheses of the positivity lemma are satisfied. Therefore, the solutions are positive, and similarly for the infected population and asymptomatic population, we reach the same results. Regarding the abundantness, we have the following theorem. Under non-negative initial conditions, the solution of the system remains uniformly bounded on the domain. For the proof, we define the M function and the integration, the addition of the populations, assuming the partial differential equation of the system and applying Green's formula with the non-boundary conditions, we reach this result, and by the Gromwell inequality, we get the following inequality, setting this condition for sigma star, and using the result by Gallegos, we demonstrate the abundantness of the solutions. About the existence and uniqueness, we can rewrite the system in this form, where H1, H2, and H3 are the corresponding nonlinear reaction diffusion operators, and define the following Banach space setting. Define the closed convex bounded wall. So we use a theorem to show the fixed point in its applied form. So we have the Banach space, and B is closed, convex, and bounded. If the function B is continuous with relatively compact image, then the function F has at least one fixed point. Here we can see that the conditions are satisfied, and the relative compactness is satisfies also. So the family is equicontinuous, and by the Arcelus-Colli theorem guarantees an uniformly convergent subsequence and the image is relatively compact. In addition, the theorem exists under the conditions given and the shorter constraints on this term, at least on one positive solution, exist in the defined ball. About the stability analysis, uh, we introduce small perturbations about the any equilibrium point, and here we can see the linearization process in the standard form, and of course the stability implies all eigenvalues of theta have negative real parts. So this is the standard process. The values of the elements of the matrix are given by this form. In case of the dynamic equilibrium, for the disease-free equilibrium, the Jacobian simplifies in this form. Okay, the characteristic equation at the endemic equilibrium takes the Hornian form, and here we can see the Root-Horowitz criteria. The endemic equilibrium is locally asymptotically unstable if and only if these conditions are satisfied. Okay, if we set these values of in the model, we can reach the bifurcation setting the row 3 yields this bifurcation value, and the system is stable for this case, and is stable and is unstable for the other side. And for the purely temporal model, the bifurcation value is less than this value. So the diffusion enlarges the stability range of the treatment parameter. And for these cases, we can see that the Rod-Horowitz conditions are satisfied, and therefore the stability is reached. Here we can see the stability regions where in this case is without a delay, and in the right hand we can see the delay effect. So we can see the difference. This is for the endemic equilibrium, and for disease-free equilibrium, this is for the without delay, and this is the case for with delay. So here we can see that delay shrinks the stability region for the endemic equilibrium in a largest parameter space must satisfy the Root-Horowitz conditions when tau is equal to 0. And for the disease-free equilibrium, the delay expands to stability regions, and the delay helps to maintain the disease-free state. As physical interpretation, the diffusion supports stability. Delay has a dual role. It destabilizes the endemic equilibrium, while the simultaneously reinforces the stability of the disease-free state. Okay, here we propose the finite difference scheme based on Meeken's rules, and this scheme satisfies the Meeken's rules for non-trivial denominator functions and non-local approximation of nonlinear terms. So we can use the Meeken's. Here we can see the theorem about the positivity preservation. The discrete scheme preserves conditional positivity if these conditions are satisfied, and then the following values are positive also. The proof is very simple. We can observe that in the equations of in the scheme, the numerator is positive, the denominator is positive. So this condition is satisfied, and the same argument applies for the infected and asymptomatic population. So since the non-negative term appears in the right-hand side of the scheme, non-negativity in the initial condition then guarantees positivity for all values of n. Talking about the stability analysis in terms of the von Neumann criteria, if we should substitute this equation in the scheme for S, we can see that this parameter is less or equal to 1, so satisfy the unconditionality for all positive delta t and delta x, and the same bound holds for infected and asymptomatic people. Talking about the consistency analysis, if we apply Taylor expansion around xi and tn for the S equation and substituting this I and Si plus minus 1 yields after a very long simplification and setting delta t equal to delta t cube and taking delta x tends to 0, the scheme reduces exactly to the continuous partial differential equation, and therefore the scheme is consistent. And the same argument applies to the infected and asymptomatic cases. So in summary, the positivity preservation is unconditional. The stability in terms of von Neumann criteria is unconditional, and consistency is valid for this order. Finally, let's review numerical simulations. So we propose these initial conditions and these parameter values for disease-free equations and endemic equilibrium, and with these grid parameters. Here we can see the 3D graph for the disease-free equilibrium points, and also the 2D line graph for the three state variables. So for this case, disease-free equilibrium, where the basic reproductive number is less than 1, the susceptible population remains stable over space and time at this steady susceptible level, the infectious pressure, and the infected and asymptomatic populations goes to 0. The same case for the 2D line graphs. Here we can see the results for the endemic equilibrium points. And this is the 3D graphs. And the 2D line graphs where the infected and asymptomatic people are different to 0. So the susceptible population, the majority is the majority, but gradually diminishes due to the constant exposure to infection. The infected population increased sharply at early stage and stabilized at the endemic level, and the asymptomatic fraction remains small relative to susceptible and infected population, but plays a significant role in sustaining transmission. The 2D line graphs confirm the convergence to a positive endemic steady state, consistent with the analytical predictions for the basic reproductive number greater than 1. Finally, we can see the effect for different time delays, of course, for the endemic equilibrium case. So we can see that for the susceptible population, gradual decline is infection spreads over time. The rate of decline is modulated by tau. The infected population increase with larger delay. Infection incidence becomes more prominent as development disease takes longer to manifest. And the asymptomatic population is more persistent with delay, latency, and the undetected case prolonged the epidemic. So we can conclude that large time delay tau slow convergence to equilibrium and increases diseases persistence, highlighting the critical importance of early diagnosis and treatment initiations to reduce the time delay. Okay, as conclusions, successfully extended the classical delayed HIV ODA model to a four-compartment spatiotemporal reaction diffusion framework. The solutions are positive, bounded, and biologically meaningful. Existence and uniqueness establishes via the fixed point theory. Threshold dynamics, the basic reproductive number acts as a sharp threshold. Disease-free equilibrium is established for the RO less than 1, and the endemic equilibrium measures for the basic reproductive number is greater than 1. The analytical stability regions characterized by steady states, diffusion support stability. The LX has a dual role. We can calculate the bifurcation conditions for the delay diffusions versus the Fourier temporal value. And it's clear that the diffusion enlarges for the stable parameter range. We propose a numerical stem that is unconditionally positively preserving, is stable in terms of von Neumann conditions, and is consistency. We can see the delay effects where if we increase tau prolongs epidemics and slow convergence, underscoring the public health imperative for rapid diagnosis. Finally, for future directions, in terms of the model extension, we can extend to the multidimensional spatial domains, nonlinear diffusion coefficients. We can include stochastic perturbation, age structure population, and fractional order derivatives. In terms of the numerical aspects, we can propose a parameter estimation from real-world data, adaptive mesh refinement, high order numerical schemes, optimal control problems, and comparison with other positivity preserving methods. Okay, that's all. Thank you so much for your attention. And this is the selected reference. Thank you so much. Bye.